welcome everyone, and very good afternoon to all of you. Actually, after we went through design the half adder and full adder for arithmetic logic unit yesterday, today we are going to go to, for example, using the full adder, okay, 4-bit full adder, to do addition for 2-bit number or subtraction. So how we are going to do that using the full adder. That's the design of full adder. We finished. Now we are going to take example. Let me suppose we have example 2 number, which is A equal to 1011, B equal to 1101. Of course, the number it will be from this is to be A3, A2, A1 and A0. So this will be the lowest significant bit, and this will be the most significant bit. A3 will be most significant bit. Same for B. Let me take an example for B is 1110. So if we do want to add these two numbers, the full adder is going to take 3 bits. Okay, now these are 2 bits, 2 inputs, so it's going, this is input 1 and this is input 2, or this is 1 and this is input 2. What about the third input? Actually the third input, it's the carry in. As you remember when we designed the full adder yesterday, so we have 3 input and 2 output. The 3 input is X, Y and C in, which is carry in, and the output would be summation and C out, which is the carry out. And that's the full adder. Now if we design, we have a 4, because these are 4 numbers, so we do need the 4 full adders. These are 4 full adders. So this is the first full adder. So we have what is it? We have A0 is 1 and B0 is 0. This is 1 0, and we have C in. Always in the full adder, when you do addition, the C in always is going to be 0 at the beginning. So we are going to put here, this is, let we go for A. What we have? We have 1 for A0, so we are going to put 1 here, 1 here, and what is this one? Here is 0, we are going to put it here, and the A3, this one, the most significant bit, we are going to put it here. Same for B, we are going to distribute it among the full adder, so this is 0, and this is 1 here, and 1 here, and 1 here. Now if we proceed the addition, so as you know, the full adder, as I mentioned just a few seconds, so you have now, if we always start with Cn, always this is Cn must be 0. So these are 3 input bits. What's the output? So the output, it will be summation, and the C out, or we name it C1, from the first full adder. Actually the C1, it will be as the input for the second full adder. So this is output for the first one, but it will be input for the second one, and these are the other 2 inputs. So, and will be sum and output from second full adder, and this output will be input for the third one, and same for the last one. So now if we do addition, 0 plus 1 plus 0, so this is in binary, it will give you 1 as a summation, and carry out is 0. Okay, there is no carry out. 0 plus 1 is 1, plus 0 is 1, still 1, and there is no carry out. Now this is 0. Then what we have? We said this is 1 and this is 1. So 0, and this, the C out, it will be C in for the second full adder. So this one, it will be 0 plus 1 is 1, plus 1, so it's 2. 2 in binary actually is 0. This is the summation is 0, and there will be carry out is 1. This one will be as a C in carry input for the third full adder. So 1 plus 0 is still 1, plus 1, so it will be 2. 2 in binary it will be 0, and the C3 it will be 1. This one will be as an input for the third, the last full adder. So 1 plus 1 is 2, plus 1 is 3. 3 in binary, so it will be 1 1. So 1, and the carry out C out is 1. Now that's if you see it, so this is 1 0 0 1, and you could know that final result for this example is 1 0 0 1, which is 9, and there is carry out is 1. As another example for you to practice, I want you in same way, if you have two numbers A and B, where A is 8 which is 1 0 0 0, sorry, 1 0 0 0, yes, 8, and B is 12. You change B to binary. So I want you to practice this one as a full adder. So A, so if it's A 1 0 0 0, so this will be 0 0 0 and 1, and B is 12. How you do 12 here? And just remember, Cn at the beginning always when you do addition, this is 0. So I want you to practice to add these two numbers and see the results. It's just for you as a practice. Now I am going to move on to the subtraction. So now if you are going to subtract two numbers, before I go to subtract two numbers, I want to give you idea about and remind you about the procedure what we did last week. You remember last week, at the end of last week, when we did subtraction of two numbers. I will go to the slides for the last week when we did subtraction. Now these examples we took it last week. The arithmetic logic unit is going to work for subtraction like this. When you do, for example, 7 minus 6, actually arithmetic logic unit will not understand 7 minus 6. He will not write it 7 minus 6. He will write it as 7 plus minus 6. Okay, or 3 plus minus 5. That's how it's going to work with arithmetic logic unit. So however, the arithmetic logic unit is going to proceed on full adder, but it's going to be as a kind of summation actually. So what's going to take? It's going to take the first number. The second number is going to take the 2's complement. So it's going to be twisted and add it to 1. That's what's going to do. This is the idea. It's going to work for arithmetic logic unit. So take the first number and B twist the second number, add to that one. This will be 2's complement for second number. So I will go back to the slide again for the subtraction, and I want to explain, I remind you about the truth table for XOR gate before I proceed to the subtraction, because it's kind of related. I'll show you how. Now if you have a X and Y, okay, and this is the truth table of course for XOR gate. So if you have X and Y, you remember for XOR gate, if the two numbers are similar, if it's 0 0 or 1 1, so the result is 0. Now if the two numbers are different, so if it's X0 Y is 1, or X1 Y is 0, so the result is 1. So that's, you remember it from yesterday lecture actually. Now if you notice, if it's X is 0, so here X is 0, okay, Y is also 0. If X is 0, sorry, if X 0 and Y is 0, the result is 0. If X is 0, Y is 1, the result is 1. However, if the X is 0, okay, the results, the results is exactly same like Y. So if it's X0 Okay, so the results is, if y is 0, so the result is 0. If y is 1, the result is 1. Now if x is 1, the result is inverse or p-twist of y. So if it's x1, look to the results. If y is 0, result is 1. If y is 1, result is 0. However, we are going to take benefit from this idea. We are going to fix one of the number. If we fix it on 0, so the results is not going to be changed. The results of q, okay, it will be exactly same the results of y. Now if we put x, we fix it on 1 and put it through XOR gate. We put x in 1 and we put it through XOR gate. So the results, it will be opposite. The result will be opposite to what y results. Okay, I am going to draw it here. Just a second. As I draw this explanation, and now I draw it. As I draw, now if x equal to 1, equal to 1, this is x. Look to the results of q. The results of q, always it will be y invert. So if x is 1, q and y is 0. Look here, y is 0. What is the q? Q, it will be opposite of y. P twist of y. So q, it will be 1. Now if it's y1, q, it will be p twist of y, which it will be 0. So that's, if you put two number and you fix one of these two number on 0, so the results of y, it will be same. The results of q, it will be same like y. Okay, if we fix it on 0, so fix this one on 0, q, it will be same like y. So if y is 0, q is 0. If y is 1, q is 1. Now if we fix x on 1, look here, we fix x in 1, so the results of q, always it will be p twist of y. So if x is 1, so if y is 0, q is opposite, so it will be 1. If it's y is 1, q, it will be opposite, that will be 0. Now this benefit, we are going to gain it to use the subtraction. We are going to take same number to realize the difference. Same number as we took it on addition. See here, same number, 1011 and 1110. I think this is b is little bit different. Okay, little bit different. Anyway, we took this number. Now how to do the subtraction. First of all, I want to do a minus b. Okay, I'm going to do the full adder, same like as I did it previously when I add two number. So I am going to do subtraction now. So a, this is going to be like this. This is a is, now first of all, a is 1, and this is a, this is the low significant bit. I'm going to put low significant bit here first. A is 1. Then after that I'm going to put 0. Then after that 1. Then after that 1. That's no doubt about it. Now for this one, for b, I want to add a plus minus b. Okay, so how to make minus b? I am going to, so b, what is b? B is 1, 1, 0 and 1. But do you remember when we did subtraction, I said first of all I have to b twist, which mean I have to, for example, I have to take the invert of 5. If it's 5, 1, 0, 1, so I have to put here 0, 1, 0. So b twisted, and then add to that 1. So that's what I have to do. Now if I go back here, how to convert? So this one, I have to be twisted. I have to make it 0. This one, I have to make it 0. This 0, I have to make it 1 in order to do subtraction. Then I have to add it with A. So how to change this one to opposite? I am going to add XOR gate. By adding XOR gate, okay, and fix the second number on 1. See here, second number, I am going to fix it on 1. If I fix on 1, okay, whatever Y here, so the result of Q, it will be twisted. It will be opposite. So if I fix on this one on 1, if Y is 0, so Q, it will be the result, the output of this one, it will be 1. If Y is 1, the result, it will be 0. So that's what I am going to do. Put here XOR, okay, and I am going to fix this one on 1, same like this. So the result, so fix this one on 1, the result of output, it will be opposite of this number. So putting XOR here and fix it on 1. So here is 1, here is 1, here is 1, here is 1. So we could put it all in one line from here. See here, this one, and put it all in one line. So, and make it as a 1. This is 1 here, 1 here, 1 here, 1 here. See, all in one line, and make it as 1. Now, if you put it here 1, okay, so whatever value here, the output here, it will be opposite of this one. So because it's 1, so output here, it will be opposite of B1, B0. B0 is 1, so the output is 0. Now here is 1. If this one input is B1 is 1, so the output should be 0. Now the input here is 1. The input here is 0. 0 XOR 1, the output will be opposite of 0, or invert of 0, which is 1. So that's how inverted. But it's not only that. Do you remember when we did subtraction? It's not only B twist. I have to B twist, and then I have to add 1 plus 1 because it's 2's complement. So we have to add this number plus this number, which is 3, plus the 2's complement of 5. 2's complement is not only B twist 5, B twist and add 1. So what about add 1? How I do add 1? To do add 1, so I have to put the C in for this one, carry in, I have to put it 1. So I will add 1 plus this plus this. So 1 plus this plus A0 plus the B twist of B0, so it will be the result of minus. So I am going to take, so I get this number, and by putting C in, start with 1, so the result, it will be like I'm going to do this number minus this number here. Okay, so that's actually the idea of subtraction. Now to make it more, better design, so if Cn is 1, and here all the numbers is going to fix on the XOR is going to be fixed on 1, so it's possible Cn, and with all this one, connect it, all of them together, and make it with something called modulator. This modulator, we are going to fix it on 1. So if the modulator is 1, so this will be, subtraction. If modulator is 1, so this will be subtraction. Now if modulator is 0, what will happen? Cn will be 0, okay? And this one, you see here, if modulator is 0, so this one it will be 0, this one it will be 0, this one it will be 0, this one it will be 0. All of these, it will be instead of 1, it will be 0. Now if you put on XOR a number with 0, what would happen? If we go back just one slide, so if I put x1, if I put x, fix it on 0. Now I am going to fix it on 0. This is fixed on 0. What will happen? Now if x fixed on 0, the results of output, okay, it will be same like the results of what you input, same. So if you fix it on 0, so the results of Q here, it will be same like y. So if this 0, it will be 0. If this 1, 1, so this is 1. So if you fix x on 0, the results of the output here, it will be q equal to y. See here? Q equal to y. That's the results. Now if I go back here, if I put this one 0, so if you put this one 0, so the output of this one, if it's 0, so the output will be exactly same like B0. So this will be 1. If you put this one 0, the output here, it will be 1. If you put this one 0, the output here, it will be 0. See, similar like B2. And if you put this one 0, the output will be similar like B3. However, if you put all of these 0, and you have carry input 0, so what is this one become? It will become subtraction. So the better design is you do it like this with XOR. They found it to do arithmetic logic unit design like this with XOR. And if you put the modulator as 0, so you are going to proceed, actually you are going to proceed summation. If you put the modulator as 1, so you are going to proceed subtraction. So let me proceed these two numbers here. What we have, if we put modulator as 1, so it's subtraction, because we are going to subtract these two numbers. So this is 1 plus 1 is 2 plus the b twist of b1, which is 0, so it will be 2. 2 in binary, actually the result is 0 and there is carry is 1. 2 is 0 and carry 1. Now this is 1 here, so 1 plus 0 plus 0. 0, this one 0, it will be invert of b1, which is y, because 1 XOR 1, so the result is, it will be opposite, which is 0. So we have carry in here for this one is 1 plus 0 plus 0, so the result is 1, and there is carry out is 0 here. Now this is 0 plus 1 plus 1, so it's 2. 2 is 0 and there is carry out is 1. Okay, then after that what we have, 1 plus 1 is 2 plus 0 still 2, so 0 and there is carry out is 1. Now the result here is 0 0 1 0, but there is carry out in C4 is 1. That means if there is carry out is 1, do you remember when we did the subtraction? If there is carry out here is 1, what does that mean? That means the result is positive, because the carry out is 1. If there is no carry out, 0 carry out, okay, if there is 0 carry out, that means you have to take the 2's complement of the results in order to get the final results. So now here, if we get back here, so the result is 0 0 1 0, and there is carry out, so the result is 0 0 1 0. Now if the result is 0 here, so you have to take the 2's complement to this one. We have another example that's for you to practice. So if you have a and b and you have two values, which is 8 and 6, just do subtraction between 8 and 6, and I want you to find out what is the final results using the full adder, for arithmetic logic units subtraction. So just do it, and if you have any question, please ask me through Google Classroom or whenever you see me during the you're coming to the university. Now let's go for another topic now, which is, you remember on microprocessor we have 3 types of registers. We said we have address register and data register and control register. You remember the control register in the practical, we name it flag register. So one of these flag registers is overflow registers and overflow flag register, and zero flag register, carry flag registers, all these registers. Now we are going to practice on overflow flag register. Just to remind you, the overflow flag register happen when you add two numbers that are positive and the result is negative, or you add two negative number and the result is positive. That's when overflow flag happen. What's happened? Now you have arithmetic logic unit design as you saw before previously. So we have 4 full adder. Okay, so that's arithmetic logic unit. 4 full adders. So just in the bit for carry out. So for carry out the on the most significant bits here, the carry out on full adder for 3. Okay, the most significant bit. You do XOR with the last carry out. So you do the most you do XOR between the most significant bit or the carry out from from third full adder with the carry out from the last full adder, which is fourth full adder. Do it on XOR. So if XOR is 1, if the result is 1, so that means you have overflow flag is on. If overflow flag is 0, that means you don't have overflow flag. So you do XOR between the carry output for the third full adder with XOR with for the carry output for the fourth full adder. If the output is 1, so that means you have overflow. If output is 0, so you don't have overflow. As easy and basic like that. When it's happened, when you have two positive number and the result is negative, okay, or you have two negative number and the result is positive. That's when overflow flag happen. Now let's go for another one, which is last thing for today lecture. So when you have a zero flag, actually zero flag, if you remember that we did it practical, it's happen when you proceed operation, let we say plus, minus, times, division, and the result is 0. So if you see here, this is NOR gate. This is the NOR gate table. So if you have NOR gate, just to remind you about NOR gate truth table. So if it's 0 and 0, okay, so the result, the output is 1. So otherwise, if it's any two numbers, 0, 1, 1, 0, or 1, 1, so the result would be 0. And that's what will happen. We are going to check the results for the first full adder, with second full adder, with third full adder, with fourth full adder, all to NOR gate. So if this 0 and this 0 and this 0 and this 0, so the results of this full adder is 0, with the results of this full adder is 0, with the results of this full adder is 0, and so on. So the output will be 1. See here, the output will be, if all of it is 0, so the output is 1. That means a zero flag happen. Okay, so otherwise it would be 0. That means no zero flag. Okay, that's it. Thank you for listening, and see you next week. Thank you. Bye.